Alright, so this is the table 5.5 that we were talking in the previous video. So here we have destination options of 3 and 8 in order. So that's where the hop by hop and the actual final destination goes. The two destination option case happens when routing headers are present. When an IPv6 packet includes a routing header, it's essentially saying this packet will visit several waypoints before reaching the final destination. Think of it as IPv6 replacement for IPv4's loose source routing option, which you saw in the big table, in which is almost never used today because of security concerns. So we discussed that in the previous video as well. We're just reiterating it because this is important. In IPv6, the routing header contains a list of intermediate nodes. Example chain, IPv6 header, then next header equals to routing, then routing header, then next header equals destination options, then destination options, then TCP header, then TCP data. Each router listed in the routing header get a turn to process and forward datagram. Second, why two destination options header exist? IPv6 designers realize something subtle. Different options may need to be interpreted by different destinations. So the first destination options header, position 3 in the table 5.5, is for options meant for the next destination. That is the current hop listed in the routing header, an intermediate node. So different options may need to be interpreted by different destinations. So some destination could reject it or some can accept it. So inside that option, we will discuss the TLV later. The first destination option header, position 3 in the table. So we will see that we will have like two destination option. So the first destination is where the position 3 came from. It's for option meant for the next destination, kind of like the next router now. It's not the final destination. That is the current hop listed in the routing header, an intermediate node. The second destination options header, position 8, is for options meant for the final destination, the end host. This allows routers or middle boxes that are part of the source route to see or act on some metadata. So any routers, hopping routers between sender and receiver, could process metadata based on their processing requirements while preserving the integrity of end-to-end data, since only the end host sees the second one. Connection to IPv6 chain and next header field. The next header field in the IPv6 base header and each extension tells you what follows. So for a packet using source routing, IPv6 header is next header equals to routing header, next header equal destination options. Destination options with have next header equals TCP, then TCP header, then TCP data. When the packet reaches the first waypoint, the IPv6 header destination address field is temporarily set to that waypoint's IPv6 address. When the packet reaches the first waypoint, the IPv6 header destination address field is temporarily set to that waypoint IPv6 address, so the destination address are temporarily set to the next router. The kernel at that waypoint processes the first destination options header, then updates. So the kernel will now then update to the next destination. Then updates the IPv6 header to point to the next waypoint and forwards it. Only when the last waypoint is reached, thus the final destination options, position 8, get processed by the true final receiver. How this connects to end-to-end checksum mathematics? Remember from before, the TCP checksum covers not only TCP header plus data, but also pseudo header, including the source and destination IPv6 address from the IPv6 header. So remember, we mentioned that the TCP header plus data, the checksum for TCP not only covers the header plus the data from its higher level, such as application data, but also of pseudo header. So aside from just TCP header, it has a pseudo header, including source and destination, IPv6 addresses from the IPv6 header. So what happens if the destination address field changes mid-route because of the routing header? The TCP checksum isn't recomputed at every hop. So because of this TCP checksum only applied to the actual data from above and its header, it isn't recomputed at every hop in the layer 3. It doesn't care what happened on the layer 3 routing, because that would validate end-to-end integrity. Instead, the checksum is computed once by the sender using the final destination address, the one that will appear in the IPv6 header after all routing headers are processed. So again, the checksum is computed once by the sender using the final destination address, the one that will appear in the IPv6 header after all routing headers are processed. The checksum is computed once by the sender using the final destination address. So it's actually computed by the sender using the final destination address, the one that will appear in IPv6 header after all routing headers are processed. So the sender kind of have made it possible as well because it targets that final destination address and computed it once, and those will be piled up by the receiving host only, or receiving host, after all the routing headers are processed by the mid-route routers. Intermediate routers temporarily rewrite the IPv6 header's destination address but not the payload. The checksum still validates correctly when the packet finally reaches the end host, because the end host reconstructs the same pseudo header with its own final address. This is a perfect example of how the IPv6 extension header chain and the checksum group math coexist. The middle header can mutate the envelope, the IPv6 header. Again, this is a perfect example of how the IPv6 extension header chain and the checksum group math coexist. The middle headers can mutate the envelope, the IPv6 header. But the end-to-end transport checksum and possibly security headers like AH or ESP guarantees that the payload's integrity is not broken. How this fits into kernel forwarding logic we discussed earlier. Just a moment, guys. So how this fits into the kernel logic we discussed earlier? For IPv6 forwarding route, what happens in kernel? It checks IPv6 header, sees next header equals to routing, then it parses routing header, updates IPv6 destination address, it decrements segments left, maybe process first destination option, then forwards packets. For the transport layer and host, only after all routing headers are processed does it receive the packet. So after all the routing headers does it receive the packet, then verifies the checksum, MAT, TCP or UDP using the final destination address. Socket layer user space. It gets the clean, reassembled, verified TCP segment. In short, the two destination option rule is there to cleanly separate hop by hop metadata. The two destination option rule is there to cleanly separate hop by hop metadata processed by intermediate nodes from end-to-end metadata processed by only by the final receiver. And the ones complement checksum group properties are what make this entire chain untransmutating process safe, because the checksum mat ensures the payload remains valid despite temporary IPv6 header rewrites. I'm just synchronizing it, guys. Oh my god, why is it not sit? I see. Yeah, it's now synchronized, guys. So an IPv6 option. So this is where the actual bits inside the this is where the actual bits inside those options that we were talking came. So IPv6 options. So as we have seen, IPv6 provides a more flexible and extensible way of incorporating extensions and options as compared to IPv4. Those options from IPv4 that cease to be useful because of space limitations in the IPv4 header appear in IPv6 as variable length extensions header or options encoded in a special extension headers that can accommodate today's much larger internet. Options, if present, are grouped into either hop-by-hop options, those relevant to every router along a datagram's path. So that's what happened, or what that hop-by-hop meaning. It means those are relevant to the mid-route routers along a datagram's path, or destination options, those relevant only to the recipient. Hop-by-hop options called hop-pop, these are the only ones that need to be processed by every router packet encounters. The format encoding options within the hop by hop and destination options extensions headers is common. So a format encoding in that hop by hop options and destination options is common, which is what we will discuss. So that's actually called TLV. The hop by hop and destination headers are capable of holding more than one options. So more than one options like this are being held by hop and destination options. Each of these options is encoded as type length value TLV according to the format like this. So the options that may be in the router or in this hop by hop and destination option, they can have multiple, or they are usually multiple of this format inside. So figure 5.7 hop by hop and destination options are encoded as TLV sets. The first byte gives the option type, including subfields indicating how an IPv6 node should behave if the option is not recognized. So the first byte, which is this option type, 0 to 8 bits, are the one responsible to check if they can be ignored or they must be accepted by the receiving router, and whether the option might change as the datagram, so this is the CHG, is forwarded. So whether that will be changed or could be changed along the way. The op data len field gives the size of the option data in bytes. So these from 8 to 16 bits provide the length of the actual data. It's kind of like its measurement of the actual data inside that option. The TLV structure shown in figure 5.7 indicates 2 bytes followed by a variable length number of data bytes. So we have these 2 bytes like 0 to 16 bits and this option data as a variable length. The first byte indicates the type of the option and includes 3 subfields. The first subfield gives the action to be taken by an IPv6 node attempting to process the option that does not recognize the 5-bit option type subfield. So these 5 bits are usually needs to be processed, but in case it is not capable, this is what the router will look at, the options. Its possible values are presented in table 5.6. Table 5.6, the 2 high order bits in an IPv6 TLB option type indicate whether an IPv6 node should forward or drop the datagram if the option is not recognized. Again, the 2 high order bits in an IPv6 TLV option type indicate whether an IPv6 node should forward or drop the datagram. So the node in the router will, this is the bit that will tell it if it will drop or not if the option is not recognized, and whether a message indicating datagram's fate should be sent back to the sender. So for value 00, and the action skip option continue processing. For value 01, action discard the datagram silently. Value 10, action discard the datagram and send an ICMP-v6 parameter problem message to the source address. Value 11, action same as 10 but send the ICMP-v6 message only if the offending packet's destination was not multicast. If an unknown option were included in a datagram destined for a multicast destination, a large number of nodes could easily conceivably generate traffic back to the source. So if an unknown option were included in a datagram destined for a multicast, a large number of nodes could conceivably generate traffic back to the source. This can be avoided by the use of the 11-bit pattern for the action field to that TLV for that option to send to the node. The flexibility of the action field is useful in development of new options. So because of this flexibility, it can be ignored or it can be accepted. It is more flexible than IPv4. And therefore it also led to the development of new options. A new least specified option can be carried in a data graph. A newly specified option can be carried in datagrams and simply ignored by those routers that do not understand it, helping to promote incremental deployment of new options. The change build, CHG in figure 5.7, is set to 1 when the option data may be modified as the datagram is forwarded. The options shown in table 5.7 have been defined for IPv6. So this CHG field is set to 1 when the option data may be modified as the datagrams forwarded. The options shown in 5.7 have been defined in IPv6. For IPv6, so this is table 5.7. It's an option in IPv6 are carried in either hop by hop or destination options extension headers. The option type field contains the value from the type column with the action and change subfields denoted in binary. So again, options like this are carried in hop by hop or destination option extension headers. The option for type field contains the value from the type column with the action and change subfields denoted in binary. So the action and change along with the is denoted in binary. The length column contains the value of the op data field, op data len byte from figure 5.7. The pad1 option so the op data length is in this length column. The pad1 option is the only one lacking this byte. So this pad1 doesn't have the length byte. So where this TLV structure goes in the overall discussion. Now remember the IPv6 header chain from earlier. IPv6 header to hop by hop options to routing header to destination options to TCP header to TCP data. Hop by hop options header, HOP, OPT, and destination options header are containers for one or more TLV encoded options. So they are container, like they contain one or more, usually multiple of these TLV encoded bits. Each option inside this header follows the type length value format shown in figure 5.7. So that figure is a zoom in on the content of one of those extension headers. Why TLV exists? Flexibility and forward compatibility. IPv4 options were fixed in size and position, which made them hard to extend and costly for routers. So it's not flexible there because they have fixed in size. IPv6 replaced them with TLV sets where type 1 byte defines what kind of option this is, like router alert, jumbo payload, pad end. So those are the type, the action, the change, and the bits. The op data length tells how long the value is, and the option data holds the actual content. Thus, the routers or endpoints can parse them sequentially without knowing every possible future option in advance. The subfields in the first byte action CHG type field. The first byte option type is not just an ID, it also encodes how routers should behave if they don't recognize the option. So it's not just an ID or 2 bits or so bits, 2 high order bits, field action, meaning what to do if unknown, skip, discard, or send ICMP v6 error. Bits 1 bit field CHG, meaning if 1, the options data may change as it's forwarded, rare. Bits 5 bits field type field, meaning identifies the specific options. This design directly connects to IPv6 goal. Routers must 5 bits is the type side field. It identifies the specific action. So what action actually this router wants to add aside from this? Do you want to expedite, to route, to fragment? And this action, neither action is not like the action you would think that the option actually wants to do with the packet, but it's actually an action and option if it cannot process this action. So this design directly connects to IPv6 goal. Router must not break when they see new features. They can decide, ignore, drop, or report unknown options without ambiguity. That's the robust extensibility IPv6 provides compared to IPv4's fragile fixed header. How it links to the destination options used twice concept. You earlier saw that destination options may appear twice in the header chain. First, before the routing header, processed by intermediate nodes like waypoints, so this or the one processed by the mid-route routers. After the routing header, processed only by the final destination. Each of these headers can contain one or more TLV options. Each option uses the format in figure 5.7 to tell intermediate or final nodes what kind of metadata this is, where it can be ignored, whether it can be modified in transit, CHG equals to 1. Thus, figure 5.7 is the schema for the payload of those headers we saw in the IPv6 header chain diagram. Again, thus, figure 5.7 is the schema for the payload of those headers we saw in the IPv6 header chain diagram. So these are the schema of the payload, of the headers, of the extension headers we keep discussing for hub by hub destination. So how this relate to kernel behavior and checksum logic? At the kernel network level, network stack level, when the IPv6 input sees next header equals to 0, hop by hop, or next header equals to 60 destination options, it iterates through this TLV structure. So the kernel of that router will iterate through these TLV structures when it sees this input path, such next header or next header equals to 60. Each recognized option, so if the router recognizes that option, it triggers a small handler like router alert, deliver packet to control plane. For unknown options are handled per the action bits. So remember, the action bits will tell how to decide on those 5 bits action, the actual action, whether it can be accepted or ignored. This happens before the TCP checksum or upper layer verification. But because these headers can alter the end-to-end payload unless CHG is equals to 1, the TCP checksum integrity remains intact. So because this header can't alter the end-to-end payload unless CHG equals to 1, the TCP integrity keeps intact. So that's how it connects to that commutative property. Example of connection in packet form: IPv6 header to next header equals to 0, hop by hop options, hop by hop options header, then option type equals to 000001060 and 10. So that means action equals to 0, it means skip, if it can be done by the 5 bits, the actual content, chg equals to 0, type equals to 0x02. So that's the jumbo payload. Of data length, so the length is 4, the option data, the actual length, 00010000, the payload length equals 65 or 64 kilobytes, and then TCP header plus data. If a router doesn't understand jumbo payload, the action equals 00 tells it to skip and continue preserving backward compatibility. In summary, how figure 5.7 connects to everything concept, IPv4 options replaced, how it connects IPv6 TLB options generalize the idea into modular headers. Concept IPv6 header chain, figure 5.6, how it connects hop by hop and destination headers that chain store TLVs format like 5.7. Concept destination option used twice, how it connects both instance of the destination options header can contain TLVs of this exact form. Checksum group math, how it connects, it ensures data after options remain verifiable end-to-end even if some options are mutable, chg equals to 0. Concept kernel to NIC path, how it connects, the kernel parses these TLVs before handing the payload to the upper layer socket, ensuring protocol behavior, router alerts, jumbogram, etc. So pad 1 and pads, IPv6 are aligned to 8-byte offset to conform with the hardware. So options that are naturally smaller are padded with 0 bytes to round out their lengths to the nearest 8 bytes. Two padding options are available to support this, called pad 1 and pad n. The pad 1 option, type 0, is the only option that lacks length and value fields. It's simply 1 byte long and contains the value 0. So the pad 1 option, which is type 0, is the only option that lacks length and value field. That's why we see it doesn't have length field earlier. It's simply 1 byte or 8 bits long and contains the value 0, so it's small. However, the pad n option type 1 insert 2 or more bytes or 2 or more 8 bits of padding into the option area of the header. So it pads it into the options area of the header using the format of figure 5.7. For n bytes of padding, the op data length field contains value n minus 2. So it still uses the TLV and it has the data len which contains value n minus 2. So where we are in this structure, so how it connects to the overall discussion. So far, we have layer, IPv6 main header, description, fixed 40 bytes, essential routing info, example, source, destination, hop limit, etc. Layer, extension headers, description, optional headers, chained via next header, example, hop by hop, routing, destination, etc. Layer inside extension headers, description, individual options encoded as TLVs. So this is what we see as the the action 2 bits and the change and the 5 bits. So now this section 5.3.1x enumerate what kinds of TLV options actually exist and what they're used for. Now how pad 1 and pad n connect? IPv6 requires all options to be aligned on 8-byte boundaries for efficient parsing by hardware and software. So again, IPv6 require all options to be aligned on 8-byte boundaries. So these are the requirements by IPv6 for efficient parsing by the hardware and software. But options vary in size. Some are 1 byte, some are 8 plus bytes. So the options inside, the hop by hop and destination, their options in TLV vary in size. So to fill the gap, IPv6 uses padding options, which are themselves encoded as TLVs. So this padding conform to the TLV format to be able to fill the gap. Now pad 1 type is equals to 0, length and data fields omitted. Just 1 byte equals 0x00. It is used when you only need a 1 byte pad to align the next option. Pad n type equals to 1 has full TLV format. Type equals to 1 and then op data length equal n minus 2, then op data length 0x00 n minus 2 bytes. It's used when you need 2 or more bytes of padding. These don't carry meaning, they're just there so the next real option starts at the correct alignment boundary in the hardware and within the hardware to be able to confirm with the right boundary for hardware and software for easy processing. So it doesn't have, both doesn't have meaning. Connection to figure 5.7, both pad 1 and pad n uses the TLV structure pad 1. Both uses the TLV structure. Pad 1 just omits the length and value field for efficiency. The rest, jumbo, payload, router, alert. So the jumbo payload are usually for is for the action bits, the 5 bits. So usually those are the high, packet that you usually put into a queue and then tell to the router that, hey, this is big and you can process it later. So each of these is another example of an option type encoded using the same TLV format. Option jumbo payload. Purpose allows 65 or 64 kilobytes datagram, jumbogram, encoded as TLV. Type equals 0xc2, len equals to 4, data equals to payload length, where appears hop by hop nodes override normal payload length equals to 0. The option for tunnel encapsulation limit, so these are all in the 5 bits. The purpose, it limits recursive tunnel encapsulation encoded as TLV, where appears hop by hop or destination option nodes like a TTL for tunnels. Option router alert for again the 5 bits. Action purpose, it tells routers this packet needs special handling encoded as TLB, where appears hop by hop nodes. Routers inspect these packets. Option quick start, again the 5 bits. Purpose, used for experimental TCP rate negotiation encoded as TLB, where appears hop by hop or destination option nodes used in private networks. Option Calypso, purpose security label for classified networks encoded as TLV, where appears hop by hop nodes used in military or banking. Option home address, purpose used by mobile IPv6 to carry home address encoded as TLV, where appears destination after routing header. Nodes required by mobile IPv6 mobility. So every single one of this fits the figure 5.7, the option type of data and option data. The only difference is what goes inside the option data and what type what value means. How this ties to kernel and header chain processing. When the IPv6 stock Linux kernel encounters a hop by hop option or destination option header, first it loops through the options sequentially. So when a kernel receives this, or the router in the kernel receives this, it will loop onto the options sequentially. For each option, it reads option type byte, option data length byte, option data of length get data length, and then based on the type value, it calls the corresponding handler like IPv6 underscore router underscore alert function or IPv6 underscore jump underscore payload function. So for padding, pad1 slash pad n, it just keeps them, they have no impact. This is a TLV parser loop, and that's what the figure and this section are describing together. So visual connection simplified. IPv6 header to next header equals to 0, hop by hop option. Hop by hop options header to that could have inside a TLV format with this. Option type equals 0x00, it means pad 1. Then option type equals 0x01, len equals to 4, pad n. Then option type equals 0x02, len equals to 4, data equals to jumbo payload size. Then option type equals 0x05, len equals to 4, data equals to router alert. The next header equals TCP or whatever. Each of those options follows figure 5 to 7 TLV's template, and all of them are described in section 5.3.1x. Why this matters conceptually, IPv6 no longer crams all extra info into a fixed 40-byte header like IPv4 did. Instead, it builds a flexible chain of extension headers. Inside each option are modular TLV records, easily added or ignored. Path 1 and Path N keeps everything aligned for hardware. Each option, Jumper, router, alert, home address, etc. provides metadata without breaking old routers because of the action bits. See figure 5.7.